Hello, my name is Sean Mccafferty. My collaborator John Berdahl and I are presenting intraocular pressure equations utilizing aqueous fluid flow and flow facility in the steady state and time-dependent domains. There are no relevant disclosures in this presentation.
The purpose of this video is to further the understanding of intraocular pressure dynamics as it relates to aqueous fluid flow. This is facilitated by mathematical modeling building upon the original work of Goldman to include glaucoma treatment, interventional outflow and inflow, as well as time-dependent pressure responses.
The teaching of students, residents, and vision scientists on aqueous humor mechanics and intraocular pressure has included a basis in the Goldman equation for over half a century. This equation was developed to explain the steady-state aqueous dynamics of a normal eye. IOP equals fluid in divided by outflow facility plus the episcleral venous pressure. We can graphically plot the fluid out of the eye as a linear function of fluid out versus IOP, whose slope is the outflow facility and x-intercept is the episcleral venous pressure. On the same graph, we can overlay the linear plot of the fluid into the eye with a slope of 0. The intersection of these two linear plots of fluid in and fluid out is the solution to the original Goldman equation of steady-state IOP, given the parameters of fluid inflow, outflow facility, and episcleral venous pressure.
Since the time of Goldman, not only has our understanding of aqueous dynamics evolved to include fluid in and fluid out and other related facilities or inverse resistances, but now we have a multitude of devices and pharmacologics which alter all aspects of fluid flow and resistance to that flow. Additionally, our understanding of aqueous dynamics has evolved to include the time-dependent, non-steady state importance of IOP to ocular health.
The real-world experimental data demonstrates nonlinear functions of fluid in and fluid out with respect to IOP where equilibrium remains at their intersection. However, there is a negative slope to the fluid in function, which is coined the inflow facility, and an x-intercept, which is at the arteriolar pressure. This was described by Moses et al. The linear assumptions are reasonably valid in the physiologic range of IOP. Therefore, the same Goldman outflow equation is used. The inflow equation is a negative sloped linear fit in the physiologic range below 50 millimeters of mercury with an x-intercept where the sloped inflow would equal 0. With this linear approach of inflow and outflow, the new steady-state IOP equation based upon equilibrium, where fluid in equals fluid out, becomes equation 4 as shown below. This equation includes the respective inflow and outflow facilities as well as venous and arteriolar pressure intercept.
There is a close mathematical analogy between the IOP curves to pressure equilibrium and the Keynesian supply-demand curves to price equilibrium. Examination of the economic mathematical derivations by a Keynes contemporary named Samuelson yields useful mathematical understanding of the time-dependent solutions in his treatise Stability of Equilibrium, Comparative Statics and Dynamics.
Given the first generalized equation at the top and its associated boundary conditions, we can develop the differential equation from the first order in the Taylor expansion. Linearization yields the solution, which is a time-dependent decay in IOP to steady state, based upon the rates of change of inflow and outflow. The time-dependent IOP equation relates the inflow facility and the outflow facility to a decay towards steady-state IOP equilibrium, given the initial values as shown in the graph below. Lastly, we can combine the steady-state IOP equation with the time-dependent equation to determine cyclical IOP changes such as diurnal IOP variation. You can do this with the addition of equations describing the time-dependent variations in inflow and outflow facility, as shown below in the graph.
Now that we have developed the basic equations, let's see how we can apply these equations with an internet-available interactive IOP lab.
The two equations, steady-state IOP and time-dependent IOP, enables a more complete description of modern ocular fluid mechanics and dynamics. These include calculation of the steady-state IOP incorporating the inflow facility in addition to the standard outflow facility. Glaucomatous disease states in which pressure-dependent altered inflow is affected are also able to be modeled. Additionally, it can predict IOP dependence upon systemic arteriolar pressure, which has been demonstrated clinically. Altered equilibrium IOP due to additional interventional outflow or inflow facilities, such as a drainage device, surgical procedures, pharmacological interventions, are all able to be calculated. The enabled model prediction of time-dependent IOP responses and its alteration due to pharmacologic and surgical interventions are critical to the modern assessment of glaucoma treatment. Finally, calculation of diurnal and other cyclical variations in IOP, including the effect of IOP interventions, are possible.
The mathematical model enables an IOP prediction in a multitude of different scenarios, allowing researchers, glaucoma treatment developers, and practitioners to gain an intuitive understanding of the delicate interconnected factors affecting IOP. The model enables the prediction of new interventional IOP responses in any possible combination. In practical terms, the equations facilitate the use of a glaucoma pressure calculator, not unlike an intraocular lens calculator. Furthermore, the calculator can be combined with machine learning to improve specific treatment modality predictions, including practitioner-specific procedures. The mathematical model is developed for demonstrating changes in intraocular pressure. However, it is applicable to any closed fluidic system with active pressure-dependent inflow and outflow processes. This can include other physiologic processes such as intracranial pressure, which has clinically demonstrated the same diurnal response variations that we see in the eye.